Alright, so in the past few weeks we have been doing Introduction to Photonics course where we learned about what? Diffraction, dispersion, interference, polarization. We learned about electromagnetic optics, we learned about fiber optics, we learned about optical amplification, optical fibers. We also learned about EDFA, that is erbium dope optical fiber. And this week we'll be focusing mostly on lasers. Okay, this is our main topic, lasers. So what is laser? Laser is light amplification by stimulated emission. Okay, that is laser. So in the past few weeks we know what is spontaneous emission and what is stimulated emission, and which one is preferable for our light amplification, that is for laser. Sorry, this will be by stimulated emission. Stimulated radiation. Okay, that is, we stimulate this, we send in some radiation and there is amplification of light. Okay, so now moving on to our very first question. What are the important characteristics of the laser? Last week we have done this. I have told you about what is an important characteristic of laser. Can you please answer? You can write in the chat box or unmute yourself and answer. There are few important characteristics by which we define a laser. What are those? Anyone can answer. Sandeep? Phase shift. Yeah. So basically, if we talk about phase, then we'll talk about coherence, right? That means laser is highly coherent. Coherent in what terms? There are two types of coherence. What are the two coherence? There is temporal coherence, there is spatial coherence. Okay? Temporal coherence is that the light is coherent over a longer time. Spatial coherence is that is light is coherent. Directionality is also one of this, correct? Okay, so I was on to temporal and spatial coherence. So temporal coherence is light is coherent over a longer time and also coherent over a longer distance. So light is highly coherent. That is, it maintains a constant phase difference for the case of laser. Sandeep has also said about directionality. What do you mean by directionality over here? What is the meaning of directionality over here? That is, it is highly directional. Okay, so in my last video, I have given an example of a torch. That is torch from your mobile phones. That is, when there is a light source, I'm sorry for this. When you have this light source, there is a wide spread of the light. But laser, as you must have seen those pencils while giving presentation, we use those laser pencils. I don't have it right now, I could have shown it to you, but you must have seen in the laboratory demonstrations how directional the lasers are. They are completely in a one straight line. That spread of the light is very small. It's quite focused, highly focused, directional and focused. Okay, focused at one point. So wherever you want to point, it points only in that direction, unlike a light from a torch. Okay. Then one of another characteristics which Sandeep has mentioned is monochromaticity. Yes, lasers are monochromatic, highly monochromatic. Okay. So that means that highly monochromatic over here, it's not that yeah, there is a single wavelength. It might be having some spread, this delta lambda, but this spread is very small. The line width, this if you have this as a graph over here, so this intensity of the laser, it's quite intense, but this spread, this line width, okay, this delta lambda or delta nu, it's very small. Okay, delta lambda, it's very small. All right. Now, what other properties is it? Yes, these are the important properties, that it is highly coherent, it is highly directional, or focused, you can say, and highly monochromatic. That is, the spread in the spectral width is quite narrow. The spectral width is narrow. Okay. Now next question. So these are the answers: spatial and temporal coherence, highly directional and intense, and narrow spectral width. Okay. Okay. Moving on to our next question. What are the basic components of a laser? I had done it in the last class. What are the basic components of the laser? And explain the components, not just name the components. Gain medium. What does the gain medium constitutes of? That is, you mean to say an active medium, right? What does the gain mediums consist of? Yes, a resonator cavity, but what does this gain medium consist of? I have told it in the last class. It consists of atoms or ions or molecules that in whose level are used for the stimulated emission. Yes, so whose level are used for stimulated emission. So that's what the gain medium consists of, such as RBM or ruby or helium neon laser. That's what the gain medium consists of my lasing medium, of what? Of ruby. What happened? Why did this happen? Of ruby, or you say helium neon laser, or any lasing medium. Okay. The next thing which he said, a resonator cavity. Okay, resonator cavity. We need to amplify our whatever radiation we are getting. Therefore, we confine, that is the gain medium over here. The gain medium is here. We confine the gain medium in this cavity, so that whatever output we are getting, it is fed back into the cavity. Okay, whatever output we get, it is fed back into the cavity. Can you give an example of this laser cavity? We have done it in the chapter interferometers. An example of a resonator cavity. It's an optical resonator. It's a Fabry-Perot cavity. Yes, it's a Fabry-Perot cavity. Yes. What else? Another component is missing. Let me see if someone has answered and I have missed out. Fabry-Perot, gain medium, resonator cavity. Okay, one more component is required. One more component is required. Pumping source. Yes, a pumping source. Why do we need pumping? This is a pump. And why do we need pumping? Why pump is used?
For excitation.
Yes. Pumping is used. Why pumping? For excitation. Or in other words, for creating a population inversion. That is, creates a population inversion. Population inversion, which is one of the condition required for lasing, for stimulated emission. Which is one of the condition required for stimulated emission. So, so these are the answers. So as far as I remembered, in the last class I have asked you to solve one question related to the number of modes available in the cavity is 4 nanometers. So did you guys answer that question? Did you solve it? I'll tell you what the question was. The question was, you have an optical resonator whose width is, or length was given. Optical resonator length was given. Okay, that was around 10 centimeters. Okay, and now I had asked you to determine what? Determine the number of modes present, okay, in wavelength range. 4 nanometers. About a central wavelength of 500 nanometers. So how did you solve this problem? I have given you lots of hints regarding this, and I've told you the answer also. So how many modes were present in a wavelength range of 4 nanometers? That is, delta lambda was given. Delta lambda is equal to 4 nanometers. Your lambda was given. Lambda was 500 nanometers. And my length of the cavity was given 10 centimeters. And I had told you to take the refractive index is equal to 1. So did you guys solve this problem? I had given you all the hints. How did you solve this problem? Tell me. Just one last step you had to do. Can anyone tell me how to solve this problem? I told you that the difference in the two frequency, that is difference in the separation between the two modes, is given by this formula. So from here we can find delta lambda. How will you find delta lambda? Because we know mu is equal to c by lambda. So delta nu is equal to minus c by lambda squared, which is delta lambda minus c by lambda squared into delta lambda. So my delta lambda would be delta lambda is equal to, I would say mod of delta lambda is equal to lambda squared by c into delta nu, which is equal to lambda squared by 2L. Why? Because c by delta nu would be equivalent to 2L from this equation. So delta nu by c is 1 by 2L. Delta nu by c is equal to, delta nu by c is equal to 1 by 2L. So I have got my delta lambda. I know my lambda. Okay. So from here you had to find this. Did you find? So separation between two modes is delta lambda. Okay. So separation between 4 nanometers. In a separation of two modes, that is in delta lambda there are 2 modes. Therefore in a wavelength range of delta lambda 1, say this is delta lambda 1, this is delta lambda 2. So how many number of modes will be there in this? Okay, so you will just give this ratio delta lambda 2 by delta lambda 1. You can say this, right? That will be equal to, how much is my delta lambda? Delta lambda 2 is 4 nanometers into delta lambda 1 is this, that is 2L by lambda square. Now you have all the information that you require. This will give you the required number of modes. Number of modes in 4 nanometers. It's just the unitary method that we solve. Okay, now just solve this. Okay. Okay, so let us move on to next problem. The answer to this would be 3 into, this will be 4 nanometers. Okay, just convert it. 3 into 3200. This is my answer. These many number of modes will be there. Okay, now let us move on to the next problem. Okay. This is my okay. The mirrors at the two ends of a laser cavity. We had said that optical resonator is one of the basic component of a laser. That is, this laser is confined between two mirrors. This is mirror N1. Say it has a reflectivity of R1. This is my gain medium. And this is again confined by another mirror, which is M2. And this M2 has a reflectivity of R2. So what should be the ideal reflectivity of this M1 and M2? What should be R1 and R2? So the question over here says, it's just a statement, you have to mark true and false. So the mirrors at the two ends of a laser cavity should have 100% reflectivity. Is it true? False. Why is it false? Okay, all of you are answering false. So why is it false?
The other
Right on?
mirror should be partially reflective to get transmission.
Yes, this other mirror, yeah, transmission is also needed. So what actually you need to extract the wavelength, right? To extract the wavelength, it's just like we are amplifying, we are oscillating. This signal photons are oscillating inside the cavity, but we don't want the photons to remain inside the cavity. There is need to extract the signal photon, So how will you extract the signal photons? You by reducing the reflectivity of the mirror M2. Okay, there is need to extract signal photons, and how to extract signal photons? By not keeping R1 equivalent to 100%. Otherwise, the laser will keep on oscillating inside the cavity, and it will not be of application to us. It will not be quite applicable. So the answer is false. No, both the mirrors should not be 100% reflective, because if the mirror at the other end, that is M2 over here, okay, if the mirror at the other end, which is M2, has a reflectivity of 100%, then we will not be able to extract the signal photons from the cavity. Okay. Now let us move on to the next question. Okay, here we have some very common data for 3 questions. So we have to go through this question very carefully and extract whatever the information over here is needed. Can you guys see the screen properly? Yeah, no, it's coming. Okay, so here we have a laser, which is a helium neon laser, and it is in a fabric parrot cavity. The length of the cavity is 50 centimeters. So we had already given about the length of the cavity. So I have taken L is equal to 50 centimeters. With the end mirrors, end mirrors has a reflectivity. So R1 is 100% and R2 is 90%. And we know the reason why R2 is 90%, to extract the signal photons from the cavity. The central wavelength of the cavity is given, that is the wavelength of the signal, whatever wavelength we want to extract, and it has a full width half maxima of 1.5 gigahertz. Okay, that is my delta nu is equal to 1.5 gigahertz. Background loss of the medium, alpha int, that is losses in the resonator cavity, that is 0.005 per centimeter. It should be per meter. I have written over here per centimeter, I'm sorry, per meter, and the refractive index is 1. Okay, so all the information required is given. We know the length, we know the reflectivity, what wavelength is the laser working on, what wavelength laser it is, and how much is the full width half maxima, that is this thing of this laser is, this is full width half maxima. How much is the full width half maxima of this laser, and what is the background loss of the cavity. So all the relevant information is given. So what are we supposed to find? The number of longitudinal modes supported by the above cavity. So very much like the previous question, very much like the question which I had given you in the last class. The number of longitudinal modes which is supported by the above cavity. So my question to you is, how will you solve this problem? What kind of thingy are you going to use? So we are given about the laser line width. Okay, so laser line width is mu FWHM is equal to how much? Gigahertz, 1.5 gigahertz, right? Okay, so this is the laser line width, and the separation, I'm sorry, the separation between the modes. What is the formula for separation between the modes? Can anyone
Delta nu
answer? Delta nu
is
is
equal
equal
to
to
C by 2L.
C by 2nL. Now n is equal to 1, so we can write this as C by 2L since n is equal to 1. Okay. So where do you get this formula? Why delta nu is equal to C by 2nL? How did you get this formula? Because do you know that we have this wavelength wave which is being radiated, and this wave has some electric field component, and we are tracking this electric field. Okay, and this electric field component has a certain phase associated with it. Okay, now this phase is actually given by 2 pi lambda into n into 2L. And what will this phase be equivalent to? Okay, I've given you enough hint. What should this phase be equivalent to for lasing to happen? What was the two conditions required? 2 pi? 2 pi what?
2 pi
2
m.
pi m. Right. So this should be equal to 2 pi m. Why 2 pi m? Because we need constructive interference. And for constructive interference, the phase difference should be this. Okay. So that's how we get delta nu is equal to C by 2nL. Okay, because how do we get this? We have to convert this uh, 2 pi gone. So n by lambda into 2L is equal to m. Yeah, this will be equal to n. Now we can use, instead of lambda, nu. Okay, what will be nu over here? This nu will be nu by c. Okay, lambda is in the denominator, that is equivalent to nu by c into what? Multiplied by m is there. So m by 2nL. So this will imply that nu is equal to m into c by 2nL, and so delta nu will be equal to that is separation between two nodes will be equal to c by 2nL. Okay, so this is the physics behind getting this. Okay, that the phase, it is actually talking about the condition of the phase, and so if you apply this formula, the number of longitudinal modes by the above cavity, we have to use this formula and then find what is the number of longitudinal modes. We know what is the separation between two nodes. Okay, and we know how much is the spread. So in the previous question I had asked you, delta lambda is given, that is delta the spread in the lambda, that is 4 nanometers. In a wavelength range of 4 nanometers, how many number of modes are present? Now in a wavelength range of this 1.5 gigahertz, how many modes are present? Just divide how many modes are present divided by the separation between two nodes. So this will give you the number of nodes, and I would urge you to go through the calculations once and let me know if there is any discrepancy. Okay, now moving on to the next question. Assuming uniform excitation along the cavity, the threshold gain is. How will you find the threshold gain? What is the formula for the threshold gain? We have been doing it. We track the electric field. In the electric field, what do we write? The magnitude of the electric field into that is times the exponential of the gain by 2 into 2L. Again, the exponential of whatever the losses are there. So, and not only we have to consider the gain, but the losses, the background losses in the system because of some absorption and scattering centers and everything present. And there, because of the reflectivity of the mirror also, there is some losses. And because my wave signal photons are taking a round trip, there will be some phase associated to it, and that phase of the electric component is given by this and here. So we'll have one of the condition. What condition? That e to the power so condition for laser oscillation. I'm sorry, I have to write over here. So what is the condition for laser oscillation? This should be equivalent to E0. So condition for laser oscillation, the condition for laser oscillation. What is your condition for laser oscillation? You just have to say that gamma L. Sorry, this should be gamma L. Okay. Okay, so gamma L exponential of gamma int, that is the loss alpha int L, okay, into R1 R2 should be equivalent to 1. We are not taking right now phase into account, we'll take that later. Okay, so this will be gamma L. Okay, and here we'll have minus sign, right? Just confirm with the book. I think yes, this will have gamma L, gamma int into multiple times L, root over R1 R2. If you take log, right, we have to take log or ln. Let's say we take ln. So ln of this minus this. This will be times. Okay, it will just have a negative sign, so this is equal to 1. So if we break this, I'm doing something wrong. Wait, I'm doing something wrong. Sorry. Here we have to take ln of this. Okay, and we take ln of 1 is 0, log of 1 of 0, and here these powers will come down. Okay, and this power will be lambda gamma L minus alpha in L minus ln of say 1 by R1 R2, and since we have a root over, so we'll have 1 by 2 over here. That is equivalent to, yeah, that will be equivalent to 0. Okay, so now gamma is equivalent to alpha int plus 1 by 2L ln 1 by R1 R2. Okay, so this is the threshold gain. Okay, so this is the condition for laser oscillation, so this must be the threshold gain, and we are given all the relevant information, the reflectivity and everything. Just substitute and you'll get the answer. Okay, that is alpha int is given, or the length of the cavity is given, which is 50 centimeters. R1 and R2 is also given. One has 100%, that is 1, and R2 is 0.9. okay, so since R2 is equal to, it's given in percentage, 90%, so R2 will be equivalent to, that implies that it is 0.9. okay, so that is ln 1 by 0.9, and just you substitute and find the answer. Okay, let's move on to the next. How do we find the photon lifetime? Average photon lifetime. So this photon lifetime, that is for the time in which it is there, it is surviving, like say. Okay, so photon lifetime is proportional to the, inversely proportional to the resonator loss. More the loss of the resonator, less will be the photon lifetime. Less the loss of the resonator, more will be the photon lifetime, because the photon will be lost if the loss is more. Okay, so that's how we define the lifetime. Okay, average photon lifetime is this. So as this decreases, TPH increases, and vice versa we have. If my photon lifetime is quite long, then it will minimize the loss. So for lasing to occur, this tau pH, if for lasing to occur, this tau pH should be as long as possible. Okay, so tau pH should be as long as possible. So this is your answer. And since we are talking about time, so we have to take distance into the velocity of the photon into account, and this velocity of the photon is given in terms of Vg in the gain medium, and for that we have to take refractive index also into account. So that will be n by alpha Rc is equivalent to this. Okay, all clear up till here? Any doubts, any questions in the previous? Okay, I'll
No.
assume that everything is fine. Okay, clear. Okay, thank you. Now, this is a very interesting question. Emission wavelength does not change with a change in the refractive index of the gain medium of a laser cavity. And when the refractive index of the cavity changes, it will alter the constructive interference condition, since the round trip phase accumulated is altered. So I want you guys to try out this question. I'll wait for a minute and see how many of you answers it. So can you guys tell me what should be the answer and your reasoning for that? A. You think both A and R are true, and R is the correct explanation of A. Okay. Anyone else? Why do you think A is true? Why shouldn't emission wavelength change with the gain refractive index of the medium? Everywhere we have refractive index into account. Yes. And why do you think, Deep Patel? Why should emission wavelength be dependent on the gain of the cavity? Okay, someone says B.
N
So,
is equal to C by nu.
sorry, say that again. You're almost close.
N is equal to C by V.
Huh?
So if refractive index changes, so wavelength will also change.
Right. True. So, yeah. So the emission wavelength, whatever emission wavelength you have for an atom, firstly it depends definitely on the band gap of the medium and also the refractive index of the active medium, as Deep Patel has already clarified, because there will be some velocity associated to the, because my this thing is traversing some distance, signal photons are traversing some distance, and in the process it will have some velocity, as we have seen in the lifetime of the photon. It will have some velocity, and this velocity will be depending on the gain medium, because n is equal to C by V. So Deep Patel is absolutely right. And definitely we have already seen that one of the conditions for this laser oscillations to sustain, or the threshold condition, is that the phase accumulated should be given by the constructive interference. So whatever phase we had associated with it, that is whatever phase 2 pi, some phase we had, what was that? 2 pi? 2 pi by lambda into n into 2l, whatever this phase that we had, this is associated with the constructive interference as this thing. So obviously depending on the laser cavity, we tell us about the separation of the modes, and also this will also tell us about how many number of modes are present in the cavity, that is C by 2nl. So that difference on the refractive index. So when the refractive index of the medium changes, it will alter the constructive interference condition because the round trip phase is accumulated, that is accumulated is altered. So the answer is D. Okay. So I want Sandeep to tell me, why did he say A? Someone said B as well. So can you guys justify? Sandeep or Balaji, someone said A. Okay, so this is the right answer. Please go through and let me know if you have any other idea or any other thing that you think there's something wrong in this. Okay, just let me know. Okay, it's all right. No problem. Okay, this is another good question. In a homogeneously broadened laser amplifying medium, so we have been told about the rate of change of in photons with respect to the cavity length, and that is directly proportional to the number of existing photons in the cavity. So the small signal gain coefficient is. So we have been given about how much is the photon flux density and how much is the saturation flux density. I want you guys to tell me, when I am told about the photon flux density, then why saturation flux density is coming into account. How do we get this saturation flux density? What is saturation signifying over here? What does saturation imply over here? I want you guys to answer. What is the physical meaning of this saturation? What happens?
Gain starts reducing after saturation photon flux density.
Yes. So I have a cavity. There is some inversion maintained in this. Okay. Here is some inversion. I pumped it. Okay. So an inversion was maintained. So now there will be radiation. This radiation, stimulated radiation. Now they will go through a round trip. Okay. Now. Okay. So what was I saying? That we have been given one important yeah, so we have been given one important information. Just a minute. Can you guys hear my voice?
Yes.
Yes. Okay. Okay, so we have been given one very important information, that the laser amplifying medium, whatever we had, the rate of change of photons is proportional to the number of existing photons in the cavity. That is d phi dz is proportional to whatever number of existing photons are there inside the cavity. So let us try to solve this. Yeah, let us try to solve this. How do we solve this? Can you guys tell me how to solve this? That is, I'm sorry. What happened? Why is this happening? So d phi dz is proportional to phi. That means there will be some proportionality constant. Let's say that proportionality constant is my gain coefficient, that is gamma. And let's say this gamma, we already know this gamma is equal to gamma 0, saturation gain by the signal photon by the saturated signal photon. Okay, we have been given information about this. So we just substitute this gamma. So d phi dz is equal to gamma 0 by 1 plus phi 0 by phi 0 saturation, that times whatever the signal photons are there inside the cavity. Okay, so now we'll just do a normal d phi by phi, d phi by phi equivalent to gamma 0 divided by 1 plus phi 0 divided by the phi 0 saturation. Okay, times what? Times dz, and we just integrate it. Here are the limits of the integration. Now this, I would ask you to answer. What would be the limits of integration? We'll integrate on both sides. What are the limits of the integration on the RHS and on LHS? Please answer. Okay, what
On
is the limit
RHS,
of...
it would be 0 to Z.
Yeah. 0 to, so we have been given the length of the cavity is d. So we'll say phi 0, that is phi of 0, phi 0, and phi of d. D is my length of the cavity. Okay, and the limits of integration on the other will be 0 to whatever the length of the cavity is, because it's an integration on dz. Okay, and dz is ranging from 0 to d. D is the length of the cavity. Okay, d over here is the length of the cavity. So if I finally integrate it and put the limits, so my ln of d phi by d phi d by d phi 0 is equivalent to gamma 0 divided by 1 plus phi 0 by phi 0 sat, and sorry, this will be phi sat, not phi 0 sat. I have been doing okay, phi sat. Okay, this is phi sat. Now what else? Times d, because it's only integration on dz. Okay, so now you know the usual mathematical thingy, so you need to do the math. Okay, and just find the gamma 0 over here. Gamma 0 will be 1 plus phi 0 by phi of sat times ln phi of d by phi 0 times what? 1 by d. So this is my answer. So just see which option is it. Here I have already mentioned that the option D is the correct answer. This option is the correct answer. Okay, now let us move on to the next question. Next question is, we know it's a homogeneously broadened medium or laser cavity. It has a length of 10 centimeters and phi 0 is 4 times 10 to the power 15 photons per centimeter square. I have been given information of phi sat as well, and phi of d. What is the saturation signal photon? What is the signal photons at the output? Again, I have to find the small signal gain of the system. How will you do this? It's very much related to the previous problem. So whatever gain we found in my previous question, that is gamma 0 is equal to 1 plus phi 0 by phi sat times ln of phi of d by phi 0 times 1 by d. So we have to use this in our question. So we have been given all the relevant information. Just substitute it and find the gain. The gain is exponential of gamma 0 times d. Alright?
We can do it by pi d by pi 0. Same answer would
How?
be there, I think.
Huh?
We can solve it by using gain is equal to phi d upon phi 0.
Gain is equal to phi d upon phi 0. Okay, let's see if we arrive at the same expression. Just solve this and tell me whatever expression you found. Okay?
What are the data? Can you show again?
Here there is some saturation as well.
Yes, so the answer is same.
Okay. Okay, we'll solve this question and then we'll see if the answer is same or not. Okay. So I'll let you know about it in the discussion forum or in the next class. Okay? So we are running out of time now. Okay, next question. A ring laser is constructed using an erbium doped fiber and is shown over here. So what are the components A, B, C, and D? I want you guys to solve this. It's a very easy problem. What is A, what is B, C, and D? We need a pump laser. Where could the pump laser be placed? Alright. Okay. So I'll solve it. D. D is the pump laser, you think? All right. Let's see what the answer is. The answer is A3, B1, C4 and D2. Okay. A3, B1, what else? C4. C4. I'll write over here, sorry. A3, B1, C4 and D2. So this is a WDM. What do you know what is a WDM? WDM is a wavelength division multiplexer. So it is used to distribute optical signals, okay, from one fiber to two or more fibers. So this is my erbium doped ring fiber, and it will distribute my optical signals from here to here, here to here. Okay. Now, now what do we have? We have a pump laser. So from here, the laser will be pumped over here. Okay. Then we have a coupler. So this will. Okay. So we have a coupler. What does a coupler do? A coupler will couple all the wavelengths that we have in different ratios. So this is a 50-50 coupler. It will couple it, and then we'll have a fiber Bragg grating. What is a fiber Bragg grating? What is a fiber Bragg grating? So what happens if you have an erbium doped fiber amplifier? So say something like this. Then you at the output, near the output, you'll have this fiber Bragg grating. Fiber Bragg grating, FBG, what it does is that it will allow only one of the light to go through it. That is, there will be gain only for one of the wavelength, and for the other wavelengths there will be loss. So this D is actually a fiber Bragg grating. That is, it will allow only that wavelength, the wavelength that we want. It will allow only that wavelength to go through. Okay, it won't allow other wavelengths to go through. So now let's move on to the next question. Yeah, this is a very easy question. I hope all of you can solve this. What is the fundamental limitation in terms of maximum power energy that can be obtained from an amplifier? We have already talked about it. The most fundamental this thing. So no matter whatever we'll do to increase the gain, at certain point there will be a gain saturation beyond which the gain cannot be increased, because there is depletion of the population inversion. Okay, so gain saturation is my answer. The next, which of these is not used? Tell me. Which of these is not a part of a short pulse amplification system? Which cannot be a part of it? We definitely, we definitely need amplification of the entire band of frequencies, and there is dispersive spread of input phase. There is dispersive compression of the output phase also, because we have this input phase. This is input. Okay, we'll have our this thing amplification, then this will be our output phase. It will be spread out in time, but so input is spread out in time, but when we get the output, it is compressed. Okay, compressed in the time. And so through two-level atomic system is not a part of a short pulse amplifier system. Next, what will be the answer to this? For achieving laser single longitudinal mode, we want only one mode. In a laser cavity, we typically prefer a mechanism that introduces loss for all other possible longitudinal modes. Instead, we can do one more thing. What is the one more thing that we can do? Increase the cavity length, operate at threshold, increase pump power, or increase signal power? So this is a very easy question.
B.
Yes, you just need to operate at the threshold such that there is only one mode available. So I would urge you to find out what will happen if we do the others. Okay, what will happen if we increase the cavity length? The separation between the longitudinal modes will increase or decrease. If L increases, then delta nu will decrease because it's inversely proportional to the cavity length. Okay, so it's inversely proportional to the cavity length, and hence what will happen if L increases, delta nu will decrease. So there will be more and more modes coming into this. If you increase pump power, what will happen, and what will happen if you increase the signal power? Just let me know. Okay, this is your homework for the next class. I'll ask this. So I have given you 2 homeworks, I guess. Okay, so thank you, class. Just let me know wherever you have any doubts or you weren't able to get the concept. Just let me know. I'll try my best to clarify all of it and help you solve these problems and clear your concepts related to the different topics that are present in the course. Thank you. Thank you so much. Thanks for your attention. So we'll be meeting the next Tuesday, and we'll talk about semiconductor sources, that is semiconductor laser sources. Thank you. Thank you, Thomas. Thank you, everyone.
Thank you, ma'am.
Thank you, Balaji.